Great. Okay, so we talk about normal form games and, of course, the motivations for game theory and the fact that lots of game can be represented by normal form games. But then this was an issue that if you consider, one player games, then we can talk about optimal strategy. Or if there is no like there is only you against the system you try to optimize, that would be just optimal strategy. But if there are games with at least 2 players, then the issue is that you cannot get the best out of it, because depending on the game, if it is a zero-sum game, your win would be the loss of another person, and the loss of you would be win of that person. So you need to find some kinds of stable solutions or stable situations or settlements that we call it solution concepts. Then we talk about the Pareto optimality as like just one concept. And that was the idea that we'll say essentially a situation is Pareto optimal or is a strategy profile. Again, a strategy profile is the vector of all strategies. And each of these strategies can be mixed or can be pure, essentially. Of course, pure is a special case of mixed as well. Then we say that is Pareto optimal if there is this strategy for this strategy profile S, there is no other strategy profile S prime which dominates it. Not a very weak, not a very strong concept, but it's a reasonable concept. And we talk about it, and there were some examples for you. Now, let's talk about another concept, which is essentially a Nash equilibrium. But before that, we need to talk about the best response. Best response, in some sense, is the optimization problem that one person can solve. What's the meaning of that? So this is the idea that the player I knows the strategies of all other players. In that case, what should I do, like as an agent I, to maximize my expected utility? So given everyone else is fixed and I know what is it, what can I do to maximize my essentially expected utility? That's called the best response. And this is, it can be 2-player game or it can be any number of players. So for this one, we are using another notation, which is an nice notation actually can be used. So here, we use S minus I. S minus Y means this is a strategy profile for all agent except agent I. Good. So in some sense, S, that was a strategy profile, minus I, remove I from. And here, it can be actually, generally, it is a vector if there are more than 2 players in the game. And it would be just the other player strategy if there are only 2 players. So if there are more than 2 players, S minus I is a vector of other people's strategies, but there are 2 people, then essentially means the strategy of the other. So in general, if you want to, if say SI be a strategy for agent I, then SI and S minus I actually describe the whole situation. And again, we are doing capital S because it is generally a vector. Good. So this is a nice notation that we are doing in game theory to say that, everyone else. Actually, minus I means everyone else. I means I, minus I means everyone else. Now, S is a best response to S minus I if, this is by definition, if for every strategy S prime I available to agent I, the utility or expected utility. Whenever we talk about utility, means essentially if it's a mixed strategy, means expected utility of the expected utility of Si is larger than or equal to expected utility of S prime. Again, both of them under the fact that other people are just using Si. So here, note that we have a S minus I. Note that here we don't have S minus I and S prime minus I. Both of them are S minus I. It means that everyone else is fixed. I want to do my best response. So there is always at least one best response. Why? Because we are just essentially something would be the maximum, and that would be the best response. And again, all things that we are talking about, unless we are mentioning explicitly, this Si or S minus I, all of them are over mixed strategies. All can be randomized. And again, we discuss about randomization is that is something that comes essentially out of history. So that's the thing that the motivation comes from that or from some other source. The people, not everything in the world is deterministic. Indeed, lots of them are randomized. Now, a best response Si is unique if this expected utility of, and again, expected utility of I under Si, while the others are playing S minus I is greater than any other utility if we replace Si with S prime I. So if he changes or she changes a strategy, then still that would be the max. Good. All drawings. So that's the concept of best response. So this, in some sense, that's the optimization part. So that is closest to the optimization. If you want to say that, okay, I want to optimize in a game, what's the meaning of that? It means that you can, at the best, you can do your best response. Because if everyone, you cannot change the strategy of others because that is chosen by others. But best response is up to you, or agent I essentially. Good. Now let's understand a little bit about best response. We discussed about Pareto optimal, and again that GPA paradox I called it. You remember that if all your grades say are 50 or above, your GPA cannot be 40, say out of 100, because we mentioned the A and A plus, and then there was some issues that A and plus are the same in the university. And the same thing, if all your grades are below 70, your GPA cannot be 8. So that's I will call it GPA paradox. And we are using that one a lot, essentially. And the whole idea is that, I mean, the average, there are some limitations for average. Average cannot be more than max or cannot be less than mean. Good. So the first thing that we want to say, that this is an important one, that always there exists a pure best response Si to S. That makes the life much easier when we prove it. Because whenever you want to find the best response, you don't need to go to the infinite case of a strategy, mixed strategies. You can just go through the table and see whether this is the best response or not. And the important thing is that, I mean, when we talk about the best response, this best response also you can check it in polynomial time, because, I mean, depending to the size of the game, but you can see whether this is better than any other pure strategies. Because one of these pure strategies should be best response, and it should be better than all others, essentially. So if you find the best one, that should be the best response by definition when we have this theorem. But let's prove this one. So to prove that, we are proving this kind of lemma, essentially. What is this lemma? This is generally the way that we are proving formally about the theorem. We have some main theorem and then have some lemmas, etc., that we are proving. So given S minus I, there are only two possibilities. I has a pure strategy Si that is unique best response to S minus I. I has infinitely many best responses to S minus I. But as you see, actually, in this case, also, if there is infinitely many responses, one of them can be pure as well. So in both cases, we will talk about both these cases, but in both cases, we have a pure strategy, and that's a good thing. And again, to see that, essentially, you can just write it. And best response is the one that we are using a lot for like a linear program. For example, in the Nash equilibrium, we will talk about it. We always talk about best response, and best response is something that you can actually solve it often with linear programming, because that's an optimization problem. Again, everything else, that was the whole idea of optimization and like linear programming or integer linear programming. Here, because we are talking about the mixed strategies, etc., everything would be also linear, and everything would be fractional. Okay, so let's discuss this one. So consider S minus I. There are only two possibilities. I want to say, either I has a pure strategy Si that is a unique best response to Si. Okay, so if it is done, if it is the case, then we are done. So assume it is not the case, essentially, the first one. Then there are two possibilities. So Si isn't unique. So if Si isn't unique, it means that there are at least greater than or equal to two strategies are best responses to Si. In this case, so this is my strategy. Good. So in that case, then it means that both of these guys should have the same expected utility, because that's the only way that you can have more than that. Then, of course, any mixture of them or any randomization of them also is a best response. So in some sense, if there are two that are equal, yeah, what is it?
No, just a question. So when you say that, so for example, you have two pure strategies, like two different actions that are the same utility, that like any extreme is that if you do like one of them half the time, the other half the time.
Yes, it can be half or any number. So essentially, if you have two, essentially mixture means this one. If you have a strategy like a S1 and like I say A1 and A2 for the actions, then you can put any P here because these are equal. So if there are two numbers that are equal, if you put it P times the first number plus 1 minus P, that's the same number. I mean, then still you get the same number essentially. So it means that you can put any probability and still you will get the same number. So if there are not unique, it means that there are two of them, and of course, any mixture of them is the one that we want essentially. The second case is that Si isn't pure at the first place. But if Si is not the pure, so these actions, if it is not pure, it means that it puts some P here for action A1, and then some 1 minus P times action A2. Good. But in this case, again, both A1 and A2 should be equal. Why? Because if they are not equal, then one of them is larger than the other. So in that case, it makes sense to move the probability toward that one. That makes the things essentially increased. So, if Si is not pure at the first place, if it's not unique, there are two of them, and mixture of them is essentially a strategy. If it's not pure, then it should be a mixture of already two ones, and this is exactly the one that if both of them are if there are two, and you will put some p here and 1 minus p here, this is, in that case, a1 and a2 should be equal. If they are not equal, you can move the mass of probability toward the higher one and you get a higher expected return. So in this case, again, means for a1 and a2 is the same, as well as any mixture of them. So of course, this is also the previous case that we have two strategies. So in both cases, essentially, we have this for both cases, essentially, we have these things that they are, I mean, there is at least one pure best strategy or best response, essentially. We call it sometimes best strategy as well. Best response or best strategy are the same. Great. Okay. So, and yeah, as you pointed out, this should be greater than or equal. So that's the meaning of best response. And that's the good thing about best response, that there is a one pure one. And again, because there is one pure one, which is the maximum, you can actually always go through the set of all possible pure strategies. And one of them would be the best. And you don't need to go to mixed one to find a pure one. And if there are more than that, then there are mixed one, of course. So let's see an example here. So say we are changing prisoner's dilemma, can always adding more actions, essentially. And this one essentially cooperate defect, or I don't know, E means does not do anything. Extra action. But it should be a extra, yeah. Extra action. Okay, so in that case, and these are the payoffs. So, and again, for normal form games, this is the one that is given to us. So we cannot force it, say that in normal form game, we should have this. This is an input to our problem. So the normal form game, somebody can model it, including ourselves, and just give it to us. Good. So, and here, for example, this is the extra actions, and this is the payoff that we have for it. This one. Okay. Now, suppose the strategy is to play action 3. Then what are the one's best response? So here we know that the 2 essentially is playing. So this is 1, and this is 2. And this is agent 1 that gets 1 more extra action. So here 2 is playing C. So if 2 is playing C, then we have 2 things. Then if the first guy is playing C, it gets 3. If it plays E, then it gets 3. And if it gets D, then it gets 5. So in that case, 5 would be the best. Suppose choose a strategy to play action D. What is the best response? So in that case, let's change the color. So it is a case. So here, you can just play C and get 0. You can play D and get 1, and get E and get 1. So in this case, we have 2 essential pairs. Versus in the previous case, we had only unique. So that's essentially the best response, and you can just check it all the time. And this is for 2 players, but you can extend it for any number of players, k players, because you just see that you will just go through the. If we have k players, let's say if we have n players, and each of them have k actions. What is the size of the matrix that we should check to find the best response? Yeah.
The maximum size of the matrix.
So the maximum size of this would be k to the n, correct? But then this is the thing. So for each of k actions that this person is doing, so you can do the k actions, but then essentially you should see what everyone else is doing. So you need to check essentially everyone else's things, that the size of that would be k to the n minus 1. Because there are all actions of the others that they are doing. And anyhow, these are some of these computational issues that you should think about, because that's the one that you will, when you want to write a program, you should see what is the size of this essentially. And it would be good, I mean, to write this. And part of this is the one that you are doing at your first project, actually, for Nash equilibrium. You need to do all of them and consider the running time. Good. So good.
So the size of that matrix is k by k to the n minus 1?
So the size of the whole matrix, yeah, it is k times k to the n minus 1. It would be k to the n essentially. That we have discussed before. Yeah. Because there are n minus 1 player. So if there are, you consider n minus other person will be n minus 1. By the way, note that here, if we know that someone else essentially, as like if we know the strategies of all other people, then in this case, as it is mentioned, there are only k choices that you need to choose. So all possible options by others would be k to the n minus 1. But if one of them is given to you as the, like a strategy of as s minus I, s minus I is given to you, then in that case, you only need to consider one of your k actions that you can. But how many s minus I? That's essentially k to the n, k to the n minus 1. So the number of these guys is k to the n minus 1. But if this is given, we check only we check only k actions. Yeah.
It's important to note that if the matrix is not squared, then we're just saying k is k max.
Yeah, k always whenever I will talk about it, I mean k is equal to k max. Yeah, because if it's not, otherwise it can be quite. Okay, so that's about this one. Now let's define Nash equilibrium. So a strategy profile S. Again, a strategy profile is the one that has is a vector of all strategies, and each of these can be mixed in general. That is a Nash equilibrium if for every I, Si is the best response to S minus I. So this is exactly the settlement concept that we have talked about in some sense. I mean, in some sense, also this kind of Pareto optimal was some kind of settlement that there is nothing better. But here, this is a bit better, I will say, concept that say, if essentially Si is the best response to S minus I. So that's the whole idea is this one. No agent can essentially do better or wants to change unilaterally or alone if others they don't want to change their strategy. Good. So he said that if everyone else taking the action, this is my action. And this is somehow essentially locked in because I don't change it because you don't want to change it. Then the next person, then in some sense, you don't change it because I don't want to change it. So in some sense, everyone is locked in essentially in some kinds of setup. Yeah.
The word unilateral means like only by themselves.
Yes. Unilaterally, that it is used a lot essentially in game theory. Yeah.
So that just means along in the matrix, along the axis that is parallel to the action profile, I think is the name. So like in here, if the player one were to go unilaterally, that would only be going along this axis of the matrix, right?
Yeah, I mean, generally unilaterally means, I mean, like if I change my action, the same thing as the best response, then I don't get anything better essentially. So each agent goes through the set of actions that she or he has.
Okay, so
Yeah, it is not just this one, also this one. All of them should be considered. Yeah, exactly. Any other questions? Great. So this is a theorem by Nash. Every game with a finite number of agents and actions has at least one Nash equilibrium. So it should be a finite. And both of them actions and the number of essentially the number of agents and the number of actions, then there is at least one Nash equilibrium. And that's a very non-trivial thing that Nash proved 1951. And indeed, this is the one that he got a Nobel Prize for. Now, how many of you have seen a Beautiful Mind movie? Yeah, I mean, yeah, that is good. So watch that one. That's a very beautiful movie. It's all about John Nash, essentially. And he has, I mean, this kind of, I mean, that is actually interesting. What do you call it? Is I think something Fernia, the sickness that he had essentially, and it is in the movie. See that I mean, always, at least sometime he sees that someone else is talking to him. That's some kind of mental sickness that he had. And this is one of the interesting things that I remember. Actually, a friend of mine heard from his student that when he got like the whole story is actually very interesting. Even after the time that the movie is essentially made, I will mention why. So that was interesting. I don't think that this is part of the movie. As I mentioned, a friend of mine heard from his student, and he said that I mean, he called the students and at like middle of the night. I say my student, like it was like very friends. I said that sorry, like I don't know, X. Do you know how can I go from US to think Switzerland or Finland essentially to Europe by ship? I say, why are you talking about like in the middle of? So because I got some award and I want to go essentially there and I'm afraid of airplane. And then he said that, okay, I don't know. I mean, probably there's a way. And he thought that, okay, maybe he again, these are some kind of imagination that he's making and they are not real because of his sickness. So he just mentioning something. Okay, why don't you sleep? We can talk more tomorrow. So, okay. So that tomorrow the students is coming as everywhere in the Princeton University that he was there. All of them essentially congratulating him because he got the Nobel Prize. So that was one interesting thing. The other things that I think this is also the time that I think movies built or made. It was Nash was still alive as far as I remember. But also the way that he passed away also was, very sad in some sense, and it is very important. I think at that time actually he took the airplane. So that was so he came to the New Jersey, Newark International Airport. If I remember, you can actually check the details more. Just search how did John Nash passed away. And then he took a cab, and in the cab, actually, he didn't have his seat belt fastened. And then the cab crashes or turn on or something like it, and he passes away because of that accident. So it is very important. Take seat belt. Essentially, put your seat belt all the time. It is very important. And it was actually, and it was even more interestingly, that flight, he got it some award essentially. So he took he went to that place, took an award, returned to, as I mentioned, he lived in Princeton or near Princeton University. And then after the award, he took the cab from the airport to go home, and this happened. So maybe if he didn't get that particular that was not Nobel, there was some other things, because when you get a Nobel, you will get some others later as well. Then if he didn't get that award, then he was still alive. But anyhow, these are just two interesting things, and you can read more about John Nash. He had done actually great things. This is a very nice thing, very important one in the game theory community. And again, his life was really very interesting, and you can see it in The Beautiful Mind, at least part of it. So I strongly recommend that you are watching that movie if you have not seen it. Good. So now come back essentially to this Nash equilibrium concept, not just John Nash, and let's check this one. So the first thing is that in which side of the road? So also note that in the Pareto optimal, there might be more than one Pareto optimal, as we discussed, because that was the whole idea, that no one should dominate it, but there might be lots of them essentially. No one can dominate. So in some sense, all of them, if you consider some kind of lattice, all of them are Pareto optimal. The same thing also for Nash equilibrium. You may have several Nash equilibrium. So consider this game. Which side of the road? Left, and right are both Nash equilibrium. Let's check that. And another interesting thing, Nash equilibrium is not always pure. That's super important. And actually, it is NP hard or NP complete to see whether there is a pure Nash equilibrium. So only the guarantee is for the existence of Nash equilibrium. And even there, we cannot find it in polynomial time necessarily. So far, we don't know a way to do that. That's actually a big open problem. There is some kind of hardness that it belongs to. So here, say that why this is a Nash equilibrium. So here, we need to check from this one. So if this guy is committing to left, then if this guy is going from left to right, it gets 0. So it's not beneficial. Now, this is from this guy, from the player 2. What about player 1? If the player 1 essentially commits to 1, then player 2, if switches, that does not help, correct? And also note that here we need to, when we consider this one, we know that the base response would be, so in some sense, when you want to consider, if we commit that other guy is doing 1, then you need to only consider the best response of this guy. And best response, there are only polynomial now. Because you can, I mean, check essentially all possibilities. So that's a good thing that we can actually check if somebody gives us an equilibrium, whether it is indeed a Nash equilibrium or not. That is exactly the one that you can also do it in your programs. That if you find it, then you want to check whether it is a Nash or not, you can check it actually. Because you only need to check the best responses at that time. But if you want to find it, you need to find these mixed strategies that might be hard. But to check it, it is easy. Or like it says, essentially best response is generally easy. Nash equilibrium in general is not easy, pure or mixed. But if somebody gives you an equilibrium and say that essentially check it, then it is easy. Because that is essentially equivalent of best response. So the same thing also here, you can take a look at it. So if this is so if this guy, the second person, is say right, then I mean this person also should do right, because otherwise the best response would be 1. Again, the best response you can, it is a pure best response always. So you can check, and this is the pure response. So it is essentially there is nothing better than that. And the same thing here, if this person is committing to 1, then this person changing this one, it goes essentially to 0. Yeah.
Would there be a Nash equilibrium in the game where it's 1, 0, 0, 1, 0, 1, 0? Because it seems like it would just keep on going in a cycle forever.
Yes, I mean there are some of them that can be that we can go there, but that means there is no pure one. There are mixed ones. That's exactly the other game that matching pennies is another game that we are talking about. Now consider the prisoner's dilemma. So in the prisoner's dilemma, so let's consider first, for example, this guy. If this person is doing C, then this person can do D. So this is not a Nash equilibrium, but the best response is not. What about this one? If this person is doing D, this person can do again D and gets 1 instead of 0. So this is not also P. What about this one? So if this person is doing 0, then if this person is essentially this person is doing C, of course, then it is not good for like. Let's consider this one. So if this person is doing 0, then this guy is not doing changing his strategy. That's why we said. However, if this guy is doing, but this should be checked from both sides. If this person is doing 5 or like 5, then this person can change from C to D and get 1. So it should be checked from both sides. Now, what about this one? So if this person is doing D, action D, so if this guy is changing from D to 0, then it gets just from D to C, it does not change it. So if this strategy of this person is to taking D, this person does not. This is the second and this is the first. So if the second player is doing D, the first player changing from D to C does not have any benefit for him or her. What about from what about from this side? So if this person is doing D here, then this person also changing it from D to C does not have any benefit, because then it gets 0 instead of. So we should check it from all sides essentially. Say everything is, and here again, you should consider any person. You should remove that person, and then consider that. I mean, again, everything is fixed. This is the best response essentially. You will consider everything fixed, and then this person I can change and say that no other strategy should be better than this one in terms of utility or expected utility. But in general, it's the pure, it will be utility. So here, as you see, that is the only Nash equilibrium. DD, essentially. Both of them essentially defect. And if you remember, as we discussed before, in the Pareto optimal things, everything else was Pareto optimal except 1, 1. Because this 1, 1 could be dominated by 3, 3. So these solution concepts may result in different, some kind of stable situations or solution concepts. So you may take one solution concept, some set of essentially strategy profile would be settlement. And if you change the concept, something else. If both of them happen at the same time, that means that you have a better concept of settlement. Sometimes this happens, for example, here, if you remember, that was not only this is not only Nash equilibrium, but also Pareto optimal. So this was a very good thing, actually. So in general, if there are more settlement for the same solution, then it means that we are in a better situation. But that does not happen all the time, because if you change the definition, then we have a different things. So it is a strict. What's the meaning of a strict Nash? A Nash equilibrium is strict if for every I, Si is the only best response to S minus I. So here it is strict if for each I, Si is the only best response. What's the meaning of that? It means that if any person unilaterally change, it will lose. In the definition of Nash, we don't say that. We say that if you take any other action, you cannot gain anything. It means that you may get the same, essentially. But in the strict case, any person should lose if he or she changes his strategy. So, I mean, if you remember, we just discussed that a best response is always unique. And it must be a pure one, essentially, or there is a pure one. So it follows that if it is a strict Nash, because there is a best response which is pure, it means that all of these strategies should be pure. Good. Because I mean, if you take any actions, I know that there's a best response which is a pure one. So what's the meaning of that? It means that at least there is this pure one. And if there is nothing else, it means that that should be pure. So that should be correct for all these players in the game. What's the good things about a strict Nash? It means that all the strategies are pure. So in that case, we can actually go through the matrix and check and see whether there is a strict Nash or not. For the Nash equilibrium in general, we cannot do that, as we will see, because we need to go to the mixed strategies. But a strict Nash, the issue is that you can check it whether there exists or not. But the catch is that it may not exist, actually. Because we know that there is a Nash equilibrium exists, but that's over all mixed strategies. So the good thing is that it is pure. The bad thing is that it may not exist. Nash equilibrium always exists, but it might be mixed. So we will see here, this is easy to see, I mean, not hard to see that. If a Nash equilibrium is pure, is not necessarily strict. Why? Because at the same time, yeah, it might be everything is pure. And in some sense, pure ones are the ones that we like the most because it's easier to find, essentially, or check or not. But it might be the case that the Nash equilibrium, when we say the Nash equilibrium is pure, it means that all strategies taken by all agents are pure. That's the meaning of pure. Pure Nash equilibrium means every strategy in this strategy profile is pure. It might be the case that the Nash equilibrium is pure, but it is not necessarily strict. Why? Because yeah, there might be two best responses that have the same value. For example, let's see some examples here. So here, this one is a strict one. Why? Because again, if you consider this person is doing this one is changing from D to C. So here, essentially, both of them, this is the DT. Because so if this person is changing from just keeping D, and this one is changing from D to C, then it gets 0. The same thing. If this guy is doing D, this guy is changing from D to C, then get it. So which one? Yeah, if this one could change from D to C, it gets 0. So either gets this one 0 or this one. So this is a strict Nash. What about if we change the numbers? If we change this one 4 or 4, still the same thing. Does not change anything. What about left and right? So here we have 2, and again, this means so every cell actually is corresponding to a action profile or pure strategy profile. So here LL. So it means that if this person is doing L, then this person is going from left to right, it gets 0. The same thing here. If this person is doing L, then this person is changing from left to right, gets 0. So all of them are pure. And this is a strict as well. What about this one? So here it is. So this is the one that we have added essentially one more to this left right. Okay. So here, if this person is doing left, this person is doing left, it gets 1, but everything else would be 0. So this is now. What about this one? If this one is taking left, this person is changing from left to right, gets 0. So this is a strict Nash. What about this one? So this person, if he's taking right, then this person, if he gets right or center, he gets 1, correct? So there is another best response. So this is a Nash equilibrium. It does not gain anything. Still it's 1. But it is not a strict Nash. Anyway, we should check also this one. If this person is doing right, this one is just changing, gets 0. So for this person is fine, but for the first player essentially changing. But if the if the second player is taking right, then the first player can actually do change it and doesn't get. The same thing also happens for this. So if this person is doing right, note that when this person is doing right, that actually is not the best. So here, what is the corresponding thing? So this is the center and right, correct? Now, if this person is doing right, then this person is going from 1 to 0. It does not get anything. Now, what about this one? If this person is doing center, then this person going from right to left gets 0 again. So here, note that so both of them are indeed Nash equilibrium, but these two are not strict. Versus this one, it is strict. Another thing, so here, if you consider this Nash equilibrium versus this Nash equilibrium, you will see actually this one is Pareto dominates this one. So this guy, Pareto dominates the second guy. Because everything is 1 here, but here is 1/2. So it means that among Nash equilibrium, again, we may have several Nash equilibrium. In that case, maybe it is the one. You may take the intersection of them. Among the Nash equilibrium takes those that are also Pareto. Because this is not the best thing. Why this guy should get 1/2, then while both of them can get 1, essentially. So these concepts, again, are there. We are talking about them. this kind of equilibrium and settlement, and you can always take the intersection. Generally, if you find some kind of equilibrium or settlement, that there are settlement according to several agreements or several definitions, that would be a better thing than just on one. Great. Yeah. So again, as we discussed here, I mean, this one, Pareto, this one, Pareto dominates this one, but still both of them are Nash equilibrium. And it is also important in the Nash equilibrium, this is up to definition. We are assuming that if everyone else does not want to change, then you don't want to change. However, it might be the case that two people can collude together. It's that because you can define such kind of definition that, like, if there are at least 3 players, if 2 players can change the things together or not. For example, here, I mean, both of these players actually can change it from 1 to 1/2. It goes to this one. That's better for both of them in some sense. So in some sense, it might be the case if you change the definition and say that 2 of them, this is concept of collude, that if 2 people can collude, they can get better. Even like there are n-2 other players that they don't change their strategy. But these 2 players together change their strategy. It might be the case that in that case, then it is not a settlement or agreement. Then they can find a better option, like this one here, 1/1/2. This is here they can actually change it to both of them, and both of them would be better off essentially in terms of this. This does not do that, but there are this concept of so Nash equilibrium is just talking about one person changing. Of course, as I mentioned, you may think, I mean, why one person? But a set of people can together essentially decide to change together. That is a very valid thing, and it is like this is a collusion essentially that can happen. However, I mean, it is like still there should be more study of Nash equilibrium and others. In general, we don't know quite well the concept of like worst case analysis versus average case analysis. Yes, so here we are considering somehow worst case that one person changes, then their situation changes. But the people may collude. The catch is that in the real world, maybe this collusion does not happen that much. For example, if you buy all from Amazon, I mean, the issue is that yes, the people may collude and get essentially make somehow Amazon screwed. Some way you can think about it, but generally does not happen because when we talk about internet, everyone just try to do selfishly and does not know what is the strategies of others. That's another issue is also that, I mean, here you can, I mean, it might be the case that even you don't know what is the strategy of others. Also, the other issue is this one that, as we discussed, for example, for this prisoner's dilemma, even if the people communicate with each other that, okay, we both change the actions, they may not essentially go according to the commitment. So in that sense, actually, you cannot, so it's not necessarily the two people colluding together is a non-trivial thing. That's the reason that Nash equilibrium makes sense that only one person changes. But in practice, I mean, yeah, 2 people can collude and can get a better things. But yeah, that's maybe in practice does not happen. Yeah.
Just based on your explanation for the third example, could you say that at the top you say you say it's the same or worse because in the example of center right, if player 2 changes from center to right, then they get 1, which is the same.
Yeah, this was for strict. For Nash equilibrium, it does not say more the things. So this is for strict that we will say that do worse. In the Nash equilibrium, it will be the same or worse. So, and these 2 were not strict. These are not strict. This was the strict. So do worse is only for strict. Otherwise, for Nash, we will say same or worse. or we say actually there is no gain. So this is equivalent of no gain. Good. So let's go to the next one, last one. So finally, this is the concept of a weak Nash equilibrium. So so if a Nash equilibrium is not strict, then it is called a weak. What's the meaning of that? At least one agent has another best response outside of the Nash. So this is by definition, if a Nash equilibrium includes a mixed strategy, then by definition it is weak. Because if as long as one of these guys are mixed, as we discussed, when you mix, you can change the probability and still get the same best response. So there are more than one best response. However, as we discussed before, if a Nash equilibrium consists only of pure strategies, it might still be weak. So these two guys that we discussed, we mentioned that they are not strict. It means that they are weak. And there are essentially, both of them are pure Nash. So of course, weak Nash equilibriums are less stable than strict Nash equilibrium. Like it is less of a settlement in some sense. So why? Because by definition, so we know that if this guy is weak, so it is weak, it means that one of them is essentially has a second best response. But as long as this person has two actions, A1 and A2, that both of them gets the same payoff, it means that it can put any P here and any minus P here. It means that only one of these all possible strategies in the Nash equilibrium, there are infinitely many which are outside of Nash equilibrium. Correct? Because it can put any P and the number of P is infinite essentially. So as long as there are another best response, then in some sense we say that this guy among infinite number of them is chosen this, but it may easily change the other one because he or she has the same payoff. Maybe there are some other consideration and changing that. So of course that means they are much less stable. And that's the thing that makes essentially weak Nash equilibrium less of settlement comparing to a strong Nash equilibrium. Good. So I think this is for now. We will continue next session about more examples. We are talking for more games and like for example, matching pennies that I mentioned. There is no pure Nash for it. And again, we really want to find pure Nash because that's much easier to find, but sometimes they do not exist. And the Nash theorem, I said that there is one, but that one might be actually a mixed one, not necessarily a pure one. So I'm stopping here.